Okay, so welcome everybody to class today. As always, you can write your name into the chat so that I have your record for attendance. I hope you've all had a very good week. I had a nice week, and and so we want to continue, talking about trigonometry, which we're going to finish up our main unit on trigonometry. So I know last week I had this problem with trying to show this graph. So I figured out what was wrong and I figured out how to do it. So maybe let me try to show you this graph that we came up with last time. So if you remember, what did I want to say? So even before we go on to anything new, if you remember, one of the things that we calculated last time was that we used data that we found online to show that this is a function that models the number of daylight hours in Ganta in 2024 as a function of the date X. So, right, this Y over here is the number of daylight hours. So the amount of time from sunrise until sunset. And this X over here is the date. And remember, our convention here was like January 1st equals 1, January 2nd equals 2, all the way up through, December 30th is going to be equal to 365, and December 31st is going to be equal to 366. Okay, so this is our convention for what these Y's and these X's mean. And so I want to show you what this graph looks like. So let me show you briefly. Okay, good. Some people are coming in. So let me show you what this graph is going to look like. So I'm going to share my screen. What do I want to see? Yes. Where is my Google? Sorry, this is weird. Oh, I see. Why is this? Oh. Let me try this one more time. Okay, let me try this one more time. I want to share this. Let me go to Desmos.com. Let me try to share my screen here. Yes, this will stop the other screen sharing. I want to do Google Chrome. There we are. Okay. So if we go to Desmos over here, so I'm going to go click on the graphing calculator at desmos.com. And so what I need to do is put in this graph. So I'll write it in again. This is Y equals 0.4245 times cosine of 0.0172 times X minus 172.5 and then plus 12.1615. I'm just copying down this function. So I can press the enter and have it graph, and it doesn't look so interesting. And actually, that's because my y-axis here is only going from 0 to 6, and most days there's between 11 and 13 hours of daylight, right? So if I go up to here, I have this, but this also just doesn't look so great because it just looks like a straight line, and that's because I don't have my axes with the correct range. So what I do to get the axes with the correct range is I click on this wrench over here. That's called graph settings. And when you click on that, you see for the x-axis, it allows you to put what is your range for the x-axis and what's your range for the y-axis. So for the x-axis, I want to put in that our range is going to be from 1 until 366, right? Because that's from January 1st until December 31st. And then for the y-axis, I want to put in, well, what's just for viewing the graph nicely, right? We should put in from, what are the number of hours in a day? Usually it's between 11 and 13. Maybe let's make the range a little bit bigger just in case it can go a little less than that. So let's say 10.5 up to 13.5. Okay. So now that I do this as my options, now we actually see the graph, and it looks like a cosine curve, in a way that actually makes sense. So if we think about, the days over here, we are starting from day 0. This is January 1st. when you have about 11.7 hours of daylight, right? This is the y-axis here. It's labeled 10 and a half, 11, 11 and a half, 12,
Ami?
and so on. Hello? Hello? Remember to please mute yourself if you're not asking a question. Okay. And then it goes up to around the 170th day of the year. So this is June over here, where you have about 12.6 hours of daylight. And then it goes back down. You're back down to 12 hours here at around the 280th day of the year. And then at the end, when you get to the end of the year, December 31st, you're back down to much less daylight, only about 11.7 hours here. Okay, so you can choose the axis ranges by putting in your numbers over here by clicking on the wrench. Okay, so this looks like a cosine curve, but basically it's scaled and shifted so that it measures this quantity that we want to measure, which is the number of daylight hours in a given day. Okay. So we're going to do this for Monrovia, okay? But I wanted to just show you, because I tried to show this last time and it didn't work. So I want to show you how it works for Ganta. Okay, so I'm going to stop my sharing. Let me mute everybody. Okay, so let me turn my iPad share back on. So share content. Okay. Let's try this now. Okay, that should be good. Okay. Great. Okay. So let's go back to the beginning now. So what are we talking about today? We want to do a little bit more on talking about these generalized cosine curves and go over this exercise that we had last time. So let's recall a generalized cosine curve is something where we're going to take y equals cosine of x, and we're going to throw in some other parameters. So we're throwing in 4 constants, a, b, c, and d. Instead, we write it as y equals a cosine of bx minus c plus d. And choosing these in the right way is going to allow us to change the amplitude of the graph. It'll allow us to change the period of the graph. It'll allow us to change the maximum value of the graph. And it will also allow us to shift the phase. So like to change where the graph takes on its maximum. And recall that if in this case you choose, a equals 1, b equals 1, c equals 0, and d equals 0, then we would just have, cosine of x, right? If I take 1 here and I take 0 here and 0 here, then this just becomes 1 times cosine of 1x minus 0 plus 0. So it really just becomes cosine of x. Okay? And we showed last time that, I have a typo here, this should be parentheses, that a plus d over 2 represents the maximum y value that you get for your graph. D minus a over 2 represents the minimum y value for your graph. And 2 pi over b is the period for your graph. And then if you take the value where the curve takes on its maximum y value, then the way you get c is by choosing it to be b times x max. Okay? So let me restate what our consequences here are. So if you want to solve for a and d here, you get that a is equal to x minimum, or x maximum, sorry, y maximum. You get that a is equal to y maximum minus y minimum divided by 2. And you get that d is equal to y maximum plus y minimum divided by 2. And over here, you get that b is equal to the period, is equal to 2 pi divided by the period. Okay, so this is how you figure out a, d, and b. And then this equation here tells you how to figure out c. So if you have data that you're going to model with the generalized cosine curve, then you need to find these quantities from the data. You need to know the maximum y value, the minimum y value, the period, and also the x value where you take on your maximum y value. And if you know all of these things, then you can figure out the constants A, B, C, and D. And if you know the constants A, B, C, and D, then you can write down your generalized cosine curve, and you can get the information basically for any data point. Okay, so what we're going to do is we're going to do this. So the homework exercise, right, was last time we saw that if we did this for the daylight hours in Ganta, then we ended up with these parameters, 0.4245, 0.0172, 172.5, and 12.1615. Okay, so we're going to do this, the same thing, we're going to do it for Monrovia. So the things that we're looking for here are going to be, we want to know what's Y max, the maximum number of daylight hours. What's Y min, the minimum number of daylight hours. We want to know what's X max. That's going to be the X value where Y takes on its maximum value. And we want to know the period, and we already know what the period is. The period is 365.25, right? That's our good approximation for how many days it takes for the Earth to go around the sun. And then the daylight hours will cycle back after that. Okay, and then from this, we're going to be able to figure out our A and our B and our C and our D. And remember, A here is going to be Y max minus Y min over 2. B is going to be 2 pi over the period. C is going to be B times X max. And D is going to be Y max plus Y min over 2. Okay, and we'll get actual numbers for these, and then we'll draw the graph again. Okay, so before we get these actual numbers, does everybody understand what we're doing? We can't figure out what the curve is until we know the actual data, right? In order to get the data, we need to actually look at the data. And what we're going to get the data is from this website, this dateandtime.info. Okay. Okay, so let's get the data. So let me find this. All right, so for this data, we're going to get, HTTPS dateandtime.info/city sunrise sunset. Okay, it's already there, but this is for Ganta, so I need Monrovia instead. So 2274895. Okay, and if you want whatever city, you just Google the name of the city and dateandtime.info, and you'll get the correct link. Okay, so here's the data now for Monrovia. Remember, the first thing we wanted to find is Y max. So Y max is going to be, certainly it's going to take place sometime in June. June is the solstice. It's the longest day of the year. So remember, we have this column over here for day length. So what's the maximum day length in Monrovia? It looks like it's 12 hours, 31 minutes, and 34 seconds. That seems to be the top here, right? It goes up to that, and then it goes back down. So 12 hours, 31 minutes, and 34 seconds. Let me just, let's write that. So that's 12 plus, so 31 minutes is going to be 31 divided by 60 hours. And then how many? 34 seconds is going to be 34 divided by 3,600, because there's 3,600 seconds in an hour. So that's going to give us 12.526. Okay, so I'll put that in. So 12.526 is the number of hours of the longest day. Okay, so now we do the shortest day. That's probably going to be in December. So I'll click here for December. Let's show what happens in December. Okay, the shortest day looks like right around here. So it looks like 11:47:45. That's how many hours. So if we want to understand the hours there, we have 11 hours plus 47 divided by 60th. So 47/60ths of an hour, and then plus 45. So that's 45 divided by 3,600. And that's going to be about 11.796. So Y min is about 11.796. Okay. Okay, now the last thing we need is X max. So we need to know the date where the maximum value is taken on. So over here, it looks like, oh, not twilight, we want sunrise and sunset, right? So it looks like the maximum day is June 19th, 20th, 21st, and 22nd. So let's just pick the date in the middle. So we'll pick, the median of these dates, basically. So we want the median of 19, 20, 21, and 22. Think back to the statistics we did in the fall. So the median of 19, 20, 21, and 22 is the average of the middle two measurements. So that's going to be 20 and a half. So we're looking for, June 20 and a half. We need to count what day of the year that is, right? So the day of the year that is going to be 31 for January, plus 29 for February, plus 31 for March, plus 30 for April, plus 31 for May, and then plus 20.5 for June. So it's 172 and a half. It's the same measurement that we had for Ganta. Okay, so X max is going to be 172.5 because that's the date of the year that we get the largest value for. Okay, so from this data, let me go share my iPad screen again. So from this data, what do we have? No, not Zoom. All right. So let's see if this is going to work. Is this working? Oh, am I not sharing? Sorry. Share content. Share screen. No, why is it not doing this? Sorry. There we are. Okay. There we are. Okay. All right. So I inputted all that data here. This is what we got from the website. So 12.526, 11.796, 172.5, and 365.25. Okay, so calculating this all, so to calculate A, these formulas just tell us what to do. So we have 12.526 plus, minus 11.7, what did I do? Ugh. Plus minus 11.796 divided by 2. This becomes 0.365. Okay, so B is 2 pi over the period. That's actually going to be the same as what we got for Ganta, so that's still going to be 0.0172. C is going to be B times X max. That's actually also the same thing that we had for Ganta. Oh, wait a minute. B times X max. Sorry, B. It shouldn't just be B. It should be B times X max. So that's 0.0172 plus a little confused. 0.172 plus times 172.5, which should be 2.96. So sorry, this actually was wrong. This should be 2.967, and this is going to be 2.967. Okay. Right, this would be 2.967. And then lastly, D is the sum of these two things over 2. So that's 12.526 plus 11.796 divided by 2. And that's going to be 12.161. Okay. Okay, so these are the parameters we're going to get. So we see they're not so different from what you get in Ganta, although the A parameter is somewhat different. So we expect in Monrovia, because it's closer to the equator than Ganta, we expect that the daylight hours will vary a little bit less in Monrovia than they do in Ganta. And that's expressed with this A parameter here, which represents the amplitude of our cosine curve, that is going to be a little bit smaller for Monrovia than it is for Ganta over here. That means in Ganta, the daylight hours fluctuate a little bit more than they do in Monrovia. Okay. So let me just do let me just graph this one more time just so we can see it. So I'll do this again in Desmos. So what do we have in Desmos here? Hold on. It's out of the way. Okay, here we are for Desmos. So I'm going to do actually, yeah, so this was a little bit wrong. This should be, this should be, 2.967. That would be right. But what we really want here instead is 0.365. And then this is all going to be the same, 12.161. And so if we do this, what we see is we get a very similar curve to what we had for Ganta, but it's a little bit flatter, right? Things only go from about 11.8 up to a little over 12.5, whereas for Ganta, they were going down to about 11.7 or 11.6, and it was going up to like 12.6. But this still gives us a curve, which, so if we want to know how many daylight hours are there on the 300th day of the year, we can just look that up, and it's going to be about 11.95. Looking it up on this graph. So this graph is going to show us the number of daylight hours for every day of the year. Okay, and because of astronomical phenomena, it turns out that these number of daylight hours act like a generalized cosine curve. Okay, actually understanding that requires some astrophysics, so we're not going to do that. But you can fit a generalized cosine curve, and we can figure out which data we need in order to make that curve work. Okay, any questions? I'll stop my share then. Let me go bring my regular thing back up. Why is this not working? It's very weird. I'm going to share my screen. Start the broadcast. Okay, good. Right. There we are. No. There we are. Taking a very long time to share. Give me. Why is this not working? It's not sharing. Sorry. Let me try this again. I am sharing screen. That's what I thought I was doing. Okay. Good. Okay. So here we are. Here's the screen. Okay, so this is all we're going to say about these generalized cosine curves, but it's nice. And if you want to do it for any city, if you want to do it for New York, you can always do it. You just have to get the relevant data over here. And then you get the, and once you have the relevant data over here, then you are able to get the important constants that you want here, and these A, B, C, and D determine your curve. And everywhere in the world, it's the same. You're just going to have different A's and B's and C's and D's. And in most places, I mean, your B is always going to be the same. And in most places in the Northern Hemisphere, your C is going to be the same because you have the same longest day. But your A and your D will be different depending on how much your daylight fluctuates and how much daylight you usually get. Okay. Okay. All right, so no questions about this. Let's move on. Okay, so there's one proof that I promised you last time before we went on to this that we skipped and we didn't have time. So I want to prove this one last application of the law of sines before we move on to our real topic today. So is this angle bisector theorem. So I'm going to draw a triangle like this, and then I'm going to draw what's called the angle bisector. So the angle bisector, so this is triangle ABC, and the angle bisector is the line from angle A down to side BC that bisects angle A. That means that it breaks it into two equal angles. Okay? And we're going to call this point D. This is the point where the line hits line BC. Okay. And so what the angle bisector theorem says is that this ratio AB over BD, so that's the ratio of this side to this side, is equal to the ratio AC over CD. Okay? And we're going to be able to prove this using the law of sines. Let's just remember what this says. The law of sines says that A over sine A is equal to B over sine B is equal to C over sine C, right? Where here we can label these sides by their opposite corners. So that's C, that's B, and this over here is A, right? Okay, so in other words, what do we have? So in other words, well, this AB is equal to side C, and AC is equal to side B, right? Okay, good. Okay, so how do we do this? Okay, so we want to somehow prove this angle bisector theorem that this is going to work. Okay, so the key observation is to notice that these angles, these red angles over here, are supplementary, right? So the red angles add to 180 degrees, and we know that sine of x is equal to sine of 180 degrees minus x. And this is true either using the subtraction formula or just because these are by using reference angles. Right, so for example, we know that sine of 75 degrees is the same as sine of 180 minus 75, which is 105 degrees, because 105 is the reference angle for 75, and if one's in the first quadrant, the other one's in the second quadrant, sine is positive in both of those quadrants. Okay, so what we know is that these red angles are equal to each other. Okay, so I'm going to call these in the proof, I'm going to call these the red angles, and I'm going to call these individual ones here the blue angles, right? So what do we have? So the law of sines for triangle ABD says what? Well, in particular, it says that that C over sine of the red angle is equal to, right, because C in ABD, C is opposite the red angle, that's equal to BD over sine of the blue angle. So this is equal to BD over sine of the blue angle. Okay, and then it's also equal to, this side over angle B, but we're not actually going to need that. Okay, but in particular, C over sine of the red angle is equal to BD over sine of the blue angle. That's the law of sines applied to this triangle ABD. Okay, the ratio of C of a side to the sine of its opposite angle is the same as the ratio of this other side to the sine of its opposite angle. Okay. Okay, so what about the law of sines for triangle ACD? Well, this says what? This says that B over the sine of the red angle, right? That's B over here over the sine of the red angle, is equal to, well, we have CD over the sine of the blue angle. Right, this is CD over sine of the blue angle, that's the opposite angle, and this is B over sine of the red angle. So what these two things both say is we can write these in terms of sine of the red angle over sine of the blue angle, right? So if C over sine red equals BD over sine blue, well, this tells us that C over BD is equal to sine of the red angle over sine of the blue angle? Right? I mean, this is just rearranging this equation, right? We divide by BD and we multiply by sine of the red angle, and we get that C over BD is sine of the red angle over sine of the blue angle. But we can do the same thing here with this equation, right? B over sine of the red angle equals CD over sine of the blue angle. If we again multiply by sine of the red angle and divide by CD, we get again that sine of the red angle over sine of the blue angle, in this case, is going to be equal to B over CD. And this C here, remember, this is AB, and the B here, this is AC. So what this shows us in the end is that AB over BD equals AC over CD, which is exactly what we wanted to prove. Okay, so this is the proof of the angle bisector theorem using the law of sines. Okay, if you have a line that bisects an angle, then the ratio of these sides to each other on the side C and side B is the same as the ratio of these sides to each other, the sides that the angle bisector cuts out along the opposite side. So these are in the same ratio as these. Okay. Good. Okay, and it comes from applying the law of sines to each triangle, which allows you to set each ratio equal to the sine of the red angle divided by the sine of the blue angle. Okay. Okay, maybe I should say that what this means is, so sine of both red angles is the same. All right, so any questions on this? Okay. All right, great. Okay. So let's go to the main topic for today, which is inverse trigonometric functions. Okay, so we'll have some time to do these. So we've seen inverse functions. So I won't say for every function, but for many functions in mathematics, we have an inverse. So the inverse function of x cubed is cube root of x. The inverse function of x minus 1 is x plus 1. And the inverse function of 4x is x over 4, right? So if I have a function, what's the inverse function? Well, informally, it's just the function that reverses what you do. So raising to the third power, how do you undo that? You take the cube root. You get back to where you started. Subtracting 1, how do you do that? Well, you add 1. You get back to where you started. Multiplying by 4, how do you undo that? Well, you divide by 4. You get back to where you started. Okay? So it turns out that the trigonometric functions also have inverse functions that undo them. So what do I formally mean with an inverse function? Well, if f of x is a function, then what is the inverse function? So this is this f inverse of x. It's called f to the minus 1 of x, but this is called the inverse function. Okay, so this is the inverse function, and that doesn't mean that it's 1 over f. So, I mean, this notation is a little bit unfortunate. Raising to the minus 1 usually means 1 over, but what this notation actually means is the inverse function. And so what the inverse function does is it reverses inputs and outputs, right? So it's the function satisfying f inverse of b is a whenever f of a is equal to b. So, for an example, let's say that f of x is equal to x cubed. Well, then f of 2 is equal to 8. That means that f inverse of 8 should be equal to 2, right? And so we see that if this is the cubing function, then what's the counterpart function that's going to send 8 to 2? That's going to be the cube root function, right? So the inverse function reverses the regular function. It takes an output and asks what input is going to give this output. And whatever input that is, that's the result, okay? So cube root is saying if I have 8, I want to know what number cubed is equal to 8. And that's going to be 2. If my function is x minus 1, I want to know what number when I subtract 1 is going to give me, let's say 2. Well, that number would be 3. How do I get that number? I add 1. So inverse functions is kind of what algebra is all based on, right? When you're solving equations, you have some expression in terms of x, and you want to isolate x. What you're really doing is just applying the inverse function to both sides. But maybe you're doing that in a few steps. Okay? So this definition is nice when the function that you start with is 1-to-1. Let's recall what a 1-to-1 function means, at least as far as a graph. That means that the graph passes the horizontal line test. Right? So it's a graph that looks something like this, where any horizontal line is only going to pass through the graph at one point. Okay, so these examples over here all pass the horizontal line test. So x cubed passes the horizontal line test. Doesn't like go up and then down. And ditto x minus 1 is going to satisfy the horizontal line test, and 4x is going to satisfy the horizontal line test. This means that, you know, there is only one real, if you have a number and I say, what number's cube is your number, you know, b, there's only going to be one number whose cube is b. And there's only going to be one number with x minus 1 equal to b. And there's only going to be one number with 4x equal to b. How do you find these numbers? You plug in b to these inverse functions. That's how it works. Now, trigonometric functions don't have this property. And that's going to complicate things a little bit. Okay? So none of these trigonometric functions are 1-to-1. So for example, we have that sine of pi over 6 is the same thing as sine of 5 pi over 6, right? And both of these are equal to 1/2. So that means if I ask you, like, what angle has its sine equal to 1/2, then, well, pi over 6 is an answer, and 5 pi over 6 is an answer. So it's not clear exactly which one should be the right answer. If I want to say, you know, what's the inverse function of sine at 1/2? Well, there's two angles that give you 1/2. So it's not clear which one we should pick. We're going to need a convention in order to do that. And what we see in terms of the graph of sine here is that this graph of sine does not pass the horizontal line test, right? If I do the graph of sine, it looks kind of like this. And if I draw some horizontal line over here, it's going to pass through the graph at many points. So if this horizontal line is, you know, 1/2, is at x equals 1/2, let's say, sorry, y equals 1/2, then it's passing through at many points, and it's going to meet the graph at x equals pi over 6, and it's also going to meet the graph at x equals 5 pi over 6, and many other points also. It's also going to be at x equals, you know, x equals minus 7 pi over 6, and x equals minus 13 pi over 6, minus 11 pi over 6. There's going to be, you know, a whole lot of points where it's going to hit the graph. Okay, so that means for sine inverse, and also for cosine inverse, and also for tangent inverse, we're going to have to kind of specify which value we actually want to take. Okay, so we're going to focus on these inverse functions for sine and cosine and tangent. Okay. All right, so how do we write it? So the inverse sine function, we call it sine inverse of x. Sometimes it's written arc sine of x. Okay, so let's just try to evaluate some values of this, right? So sine inverse of 0, sine inverse of 1/2, sine inverse of minus 1/2, and sine inverse of 2. Okay, and so remember, for all of these questions, what does it mean to do the inverse? It means we want to know here what angle has that its sine is equal to 0. Here we want to know what angle has that its sine is equal to 1/2. Here we want to know what angle has that its sine is equal to minus 1/2. And here we want to know what angle has that its sine is equal to 2. Okay, so let's start easy. So sine inverse of 0. What angle has sine equal 0? Anyone? Okay. So what angle has, if you plug it into sine, do you get 0? Anyone? Okay. Well, I mean, the answer is going to be 0, right? Sine of 0 is equal to 0, right? And now there are other angles whose sine is equal to 0. You can also have pi and 2 pi and minus pi and minus 2 pi and so on. But what angle has a sine equal to 0? In this case, it's just 0. And in fact, this is going to be the preferred value, so I'm going to circle it in red. Okay. So what angle has sine equal to 1/2? I'll just go through these for time. So pi over 6 has that sine of that angle is 1/2. There are other angles too. You have 5 pi over sine of 5 pi over 6 is also equal to 1/2. You have sine of 13 pi over 6 is equal to 1/2. Sine of negative 7 pi over 6 is equal to 1/2. There's a whole lot of angles whose sine is equal to 1/2. But the standard one that we take is pi over 6. Okay, similarly, sine inverse of minus 1/2, well, that can be sine is an odd function. What's going to give you minus 1/2? Minus pi over 6 will work. Minus 5 pi over 6 will work. Minus 13 pi over 6 will work. And then also just 7 pi over 6 will work, etc. But the standard one that we take is minus pi over 6. And sine inverse of 2, is there an angle whose sine is going to be 2? Angle whose sine is 2? Well, there isn't, right? I mean, sine is always between minus 1 and 1. So for an angle whose sine is 2, this is just going to be undefined. Okay? Let's see, yeah. So what we do in this case for sine, I mean, if we look at the graph of sine of x, here's minus 1 and here's 1, the graph of sine of x somehow goes like this, and then it starts repeating itself. I'll draw the rest in a dotted line. So if we pick an angle, sorry, if we pick a number between minus 1 and 1, and we want to find an angle whose sine is that number, right? This is y equals sine x. Then we can always pick an angle between minus pi over 2 and pi over 2. Okay, so this is our convention. Convention is that if we say sine inverse of x, well, at least when it is defined, is always a value between minus pi over 2 and pi over 2. Okay, so this is our convention. Okay, so when I say sine inverse of 0, yes, sine of pi is equal to 0, but I don't mean pi as my answer. I mean 0. Okay, so sine inverse of 0 means 0. Okay. All right, so any questions about this? Okay, everything okay? Good. Okay, so what did we learn on this? We saw that this sine inverse only takes values between minus pi over 2 and pi over 2, and furthermore, the domain consists only of the interval from minus 1 to 1, right? Anything else won't have an angle whose sine is that number. Okay, so I try to do sine of 2, there's going to sine inverse of 2, there's no answer. If I try to do sine inverse of minus 2, there's no answer. I try to do sine of 100, sine inverse of 100, there's no answer, right? There's no angle whose sine is going to be 100 degrees. So we can't do this. Okay? And so we're going to have similar issues when we do cosine inverse and tan inverse. There's going to be only certain numbers we can plug in. That's what's called the domain. Those are the numbers we can plug in. And there's going to be only certain numbers that it can take. This is what's called the range of the function, okay? There's going to be only certain values that it actually takes. So let's go ahead and do this for cosine and for tangent, okay? People seem to be a little sleepy today. So go here. All right, so what about cosine? So cosine works the same way as sine. The inverse cosine function is cosine inverse of x, or it's also written arc cosine of x. And let's do the same table that we did for sine. So if this is x, and this is going to be cosine inverse of x, right? So if I want to have, let's say, so x here is going to be 0, or 1/2, or minus 1/2, or 2. Okay, we're just going to do some various examples. So cosine inverse of 0 means, can we find an angle whose cosine is 0? So can anybody tell me an angle whose cosine is 0? Remember, it's going to be like the x x coordinate on the unit circle. So what angle has its cosine equal to 0? Time it's going to be pi over 2, right? And maybe let me write this clearly. This is because cosine of pi over 2 is equal to 0. Okay, that means since cosine of pi over 2 is equal to 0, cosine inverse of 0 is equal to pi over 2. Okay. Also for 1/2, what angle has cosine equal 1/2? That's going to be pi over 3. This is because cosine of pi over 3 is equal to 1/2. What about cosine inverse of minus 1/2? This turns out that this is going to be 2 pi over 3, 120 degrees. This is because cosine of 2 pi over 3 is equal to minus 1/2. And then cosine inverse of 2, again, undefined because there's no angle whose cosine is 2. Right, so again, undefined. Okay. And now for cosine, remember the cosine curve looks like this, where this is pi, this is 0, this is minus 1, and this is 1. This is y equals cosine x. And then there's the rest of the cosine curve, but it just repeats the same values after this. So if we want to find an angle whose cosine is a given number between minus 1 and 1, we can always take that angle to lie between 0 and pi. Okay, so our convention here is that cosine inverse of x is always between 0 and pi. Okay. So sine inverse of x was always between minus pi over 2 and pi over 2. Cosine of x is going to be, cosine inverse of x is always going to be between 0 and pi. Okay? Okay. All right. So let's see, what do we learn here for this cosine of x? We saw on the previous slide, cosine inverse of x only takes values between 0 and pi. And furthermore, the domain is also just the interval -1 to 1. It's just like inverse sine of x. Okay, the domain consists only of these numbers, right? You can't plug in anything that's not between -1 and 1 because you won't be able to find an angle whose cosine gives you that number, right? Any angle that you want to find, cosine is going to give you that number. It's going to have to be, you know, something between -1 and 1, okay? Because you won't find anything whose cosine is equal to 2 or whose cosine is equal to -3 or anything like that. Okay. Any questions? Okay, so let's finish up with tangent. Okay, so we can do the same thing for tangent. So the inverse tangent function is written this way, inverse tangent of x, or arctan of x. So we'll do our same little chart. So here we have x, here we have inverse tangent of x. So here we have 0, 1, and minus square root of 3. Okay, so let's see what angle. Do we have an app for these functions? I see a question. An app meaning like an application, or meaning like a computer program? I mean, like these on most scientific calculators, you will have these buttons on a scientific calculator. What you have to make sure is that your calculator is set to radians, because if it's not set to radians, then you might get your answer in degrees, which maybe that's okay also. Maybe that's what you want. But in order for these functions to be well defined, you have to know whether your calculator is set to radians or to degrees. Okay? Okay, so maybe okay, good. All right. So what do we have here? So tangent inverse of 0, again, is going to be 0. This is because tangent of 0 is equal to 0. Tangent inverse of 1 is going to be pi over 4, or 45 degrees. This is because tangent of pi over 4 is equal to 1. And then tangent inverse of negative root 3, that's a little trickier, but this is going to end up being 2 pi over 3. And this, sorry, not 2 pi over 3. It's going to be equal to negative pi over 3. And that's because tangent of minus pi over 3 is equal to negative square root of 3. Okay, and so similarly to sine, our convention for tangent is that tangent inverse of x takes values only between minus pi over 2 and pi over 2. Okay, so this is like sine inverse. Okay. Okay, so sine inverse and tangent inverse take values between minus pi over 2 and pi over 2. Cosine inverse takes values between 0 and pi. You couldn't have it take values between minus pi over 2 and pi over 2 for cosine, because then those angles only give you positive numbers when you take the cosine. You need a range where you get everything. So the graph of tangent, remember, y equals tangent of x, looks kind of like this. And this is pi over 2, and this is minus pi over 2 over here, right? and then the graph repeats itself over and over again. But so you can get every value, every real number. In this case, it's all the real numbers, not just the numbers between 0 and 1. You can find an angle between minus pi over 2 and pi over 2 whose tangent is going to be that real number. Okay? So what we get here for the inverse tangent function is that it only takes values between minus pi over 2 and pi over 2. However, the domain of inverse tangent of x consists, I don't want to say only, consists of all the real numbers. Okay, so using the graph of y equals tangent of x, right? Let me just draw this again. If I'm going to draw the graph y equals tangent of x, I'm going to just draw that part of the graph between pi over 2 and minus pi over 2. So we have our asymptotes here. And then the graph of tangent of x looks kind of like this. Okay, this is y equals tangent of x. And so let's say I wanted to know what's inverse tangent of 100. Well, I don't know exactly, but I could go all the way up to the point 100 on the y-axis. And I want to know tangent of 100 equals this. This is the same as solving that tangent of x equals 100. Right? To evaluate tangent inverse of 100 is the same as solving tangent of x equals 100. And now I don't know what angle satisfies tangent of x equals 100, but it's clear from looking at the graph that there is some angle where tangent of x is equal to 100, right? I mean, I can go from 100, I can draw my horizontal line over to the graph, and then I can draw this vertical line down to here. And whatever that angle is, that's going to be an angle whose tangent is equal to 100. That angle looks like it's going to be very close to pi over 2. It's probably going to be a little bit less than pi over 2. Let me actually just do it. Tangent, so if I do arctan of 100, so it turns out that this is actually going to give me x is approximately equal to 1.561, whereas if we want to know what is pi over 2 in decimals, so pi over 2 in decimals is roughly 1.571. Okay, so this tells me that tangent inverse of 100, it's going to be an angle that's very close to pi over 2. It's not quite 1.57, but it's 1.56. You know, it's very close. Okay, so tangent inverse is a little bit different from cosine inverse and sine inverse because tangent inverse you can plug in any real number you want and you'll be able to get an answer. There is an angle whose tangent is equal to 100, and there is an angle whose tangent is equal to -50, even though there's no angle whose sine is equal to 100, and there's no angle whose sine is equal to -50. Okay? So tangent inverse also only takes values between minus pi over 2 and pi over 2, but it behaves a little bit, but it behaves differently from sine and cosine inverse. So maybe I should, before I do the homework exercises, let me just do a summary sheet. Okay, so summary, right? So I'm going to have a chart. This is going to be the function. This is going to be the domain, by which I mean kind of the x values that you can plug in. And this is going to be the range, by which I mean the y values that you can get. Okay? So my function here is going to be, so I have sine inverse of x, cosine inverse of x, and tangent inverse of x. So for sine inverse, the domain is -1 less than or equal to x less than or equal to 1. And the range is going to be minus pi over 2 less than or equal to, y less than or equal to pi over 2. Okay. Okay. For cosine inverse of x, the domain, again, is going to be x between -1 and 1, because those are the only values that cosine can take on. And the range is going to be, instead of minus pi over 2 to pi over 2, it's going to be all y between 0 and pi. Okay. And lastly, we have tangent, where the domain is all real numbers. plug anything into inverse tangent. You can try to solve for it. All real numbers. And the range is, again, what are the values that it can take on? Again, it's going to be all y's between minus pi over 2 and pi over 2. Okay. So this is our summary for these inverse trig functions. Okay, and you see them all in a chart here. Okay, and remember, why are they? I mean, you shouldn't just take this as, given to you by God, right? You should understand why this is true, right? And the point is, the domain is going to be, everything here is like, what can sine of an angle be? It can be between -1 and 1. What can cosine of an angle be? It can be between -1 and 1. What can tangent of an angle be? It can be any real number. And then the ranges, these are more set by convention. So we want to know, what angles do we need in order to get every possible sine, and in order to get every possible cosine, and in order to get every possible tangent? And the answer is, you need exactly these angles to get every possible sine, these angles to get every possible cosine, and these angles to get every possible tangent, right? Minus pi over 2 to pi over 2. Okay. All right, any questions here? Okay.
Yeah. Hello,
Yes,
Doc.
Emmanuel?
Yeah, how are you?
Good, how are you?
Yeah, thank you very much. I would have you a little, whether you can please look at the inverse tangent.
Inverse tangent? Yeah.
Yeah, the inverse tangent.
Yeah. So you want this slide here? Or you want this slide? So over here, maybe just to answer the question right over here, this would be our x value that gives tangent equal to 100. And so solving inverse tangent of 100 is the same as solving tan x equals 100. So you can even think about this in algebra, right? If I have something like this, I can apply inverse tangent to both sides, and that's what isolates x, right? So in solving an equation, maybe we'll do this a little more next time, applying inverse tangent function to each side of this will give me that x equals inverse tangent of 100. So you can apply the inverse trig functions to cancel out trig functions when you're solving equations. Okay, so maybe we'll do some examples of that next time. Okay, so let me write the homework here. So there's 3 exercises. So the first one is just straightforward, just evaluate an inverse tangent here and an inverse sine.
Before the homework, sir. Hello?
Yes, Emmanuel? Yep.
Before the homework, I heard you talking about trig equation.
Yeah. So we'll do those next time.
Oh, okay.
Yeah.
Okay.
No, we'll do trig equations next time.
Okay, thank you.
Okay. Okay. So homework exercises, first, just evaluate these inverse tangent and inverse sines. So this is a little bit of a challenge. Prove this identity, that sine inverse x plus cosine inverse x is always equal to pi over 2 for all x between 0 and 1. And if you want an extra challenge, you can try to show that it's even true for all x between -1 and 1. Okay? So think about it, think about this with an example, right? If you have x is like square root of 2 over 2, then sine inverse of x is pi over 4. Cosine inverse is also pi over 4. So you win. If x is, say, 1/2, then sine inverse of 1/2 is pi over 6. Cosine inverse of 1/2 is pi over 3. You add them together, you still get pi over 2. So can you think about why this identity always has to be true? Okay, so that's number 2. And now number 3 is, suppose you wanted to define secant inverse of x, right? We didn't do we didn't do secant. We only did sine and cosine and tangent. And usually people are only using sine and cosine and tangent. But let's say that you wanted to define secant inverse of x. There's no reason why you can't do it. So the question is, how would you finish filling in this chart, right? So if I wrote secant inverse of x, what would the domain be? And what would the range be? So what values could you plug into secant of x? I mean, we want to know what numbers can you find an angle whose secant is that number? That would be the domain. And then you want to know what values of x do you need to plug in order to get all of the possible secants? That would be the range. So there's not necessarily one right answer here. It's a bit of an open-ended question. Okay? So this is just something to think about, and we can discuss it next time. All right. And on top of that, so here we are. So for next week, we're going to discuss links between complex numbers and trigonometry. We're already meeting at our usual time of 4:30. And let me say that we'll also do some trigonometric equations. So we probably actually won't have that much time for complex numbers. We'll do that more the next week. Okay, so we'll do trigonometric equations and the links between complex numbers and trigonometry. Okay, thank you as always for your attention. And if there's any last questions, I can take them now.
Yeah, that
Yes, question.
I didn't get you. I didn't get you.
When?
Just on the last word you said.
Oh, just now. Oh, I'm just saying we'll also do some trigonometric equations, and we may spend a lot of time on trigonometric equations, which means we might not have time for complex numbers next week. And if that's the case, we'll do them the week after.
Okay. Then another thing I wanted to find out that I was in the trigonometry class teaching the inverse of sine, cosine, and tangent.
Okay.
And a student asked me for the practical application of the inverse sine, cosine, and tangent. So what could be that, sir?
Okay. Well, so we'll talk about this a little bit more, but I mean, the main practical, so inverse tangent is actually the main, so let me get back to you. I mean, so inverse tangent is used all over the place whenever you want to do, when you want to do what's called polar coordinates, when you want to kind of understand coordinates in a circular system. So it'd certainly be used for navigation, for things like this. I imagine it's got some applications in some, you could ask bearings problems in a way that you have to use inverse sine and inverse cosine and inverse tangent. It's also used quite a bit in calculus, although that's maybe a little bit hard to understand right now. And it's used for waves. Let me get you a better answer to that question, like at the more appropriate level for the student. Let me get you a good answer for that question next week.
Okay, sir.
Okay.
Thank you.
All right, you're welcome. Yeah, no, I'll include a practical application next week. All right, any other questions? Okay, all right. So if there's no further questions, then I'll stop the recording.